Yo, Code Pilots, welcome to Part 10 of the Python Masterclass, Data Structures. We've tamed tries and their string magic, and now we're leveling up with segment trees, powerful tools for range queries. If you're new to the squad, no worries. Check the playlist for the basics and catch up on heaps and tries. Segment trees are like supercharged arrays, making range operations lightning fast. Grab your coding gear and let's dive into this query-filled adventure with detailed breakdowns. Let's break down what a segment tree is. A segment tree is a binary tree designed to store information about intervals or segments of an array, letting us perform range queries like sum or minimum efficiently. Each node represents a range, and the tree splits it into smaller segments, pre-computing results for quick access. For example, for an array of numbers, a segment tree can find the sum of any range in log n time, way faster than scanning the array. We'll build one in Jupyter Notebook, exploring how it handles range operations step by step. Let's get started. Why are segment trees awesome? They're key in competitive programming and real-world apps. Think of finding the minimum temperature over a week's data, or summing sales in a store over days. Segment trees handle these in a flash. They shine in scenarios needing frequent range updates or queries, like financial data analysis or game physics. With O of log n time for queries and updates, they beat linear scans hands down. We'll code a segment tree today, focusing on building it and querying sums. With a line-by-line deep dive, let's set up and build. Let's construct our segment tree. We start with a segment tree class, using an array to store the tree where each node holds a range's sum. We initialize with self.tree equals a list of zeros with size 4 times the input array length. This ensures space for all nodes. The self.build method takes the array and indices low and high. First, current equals self.tree sets the tree array. Then, if low equals high, current index equals array low sets the leaf value. Else, we find mid equals low plus high divided by 2. Build the left child with self.build array low mid, and the right child with self.build array mid plus 1 high. Finally, current index equals current left child index plus current right child index computes the sum. Let's test this with an array like 1, 2, 3, 4. After building, we'll see how nodes store range sums. Let's break down each line to understand this construction. Now, let's add the query method. We define query with start and end indices. First, current equals self.tree accesses the tree. The helper method, query underscore helper, takes node index, node start, node end, and query range, start end. If node start greater than end or node end less than start, return 0 for no overlap. If node start greater than or equal start and node end less than or equal end, return current node index for full overlap. Else, find mid equals node start plus node end divided by 2, and return query underscore helper left child plus query underscore helper right child. Testing with range 1 to 3 on our array should give sum 6. Let's explore each line's role in this recursive query. Let's apply this to a practical example. Tracking running sums. We define update to modify a value, then query ranges. The update method takes index and value, setting array index to value, and rebuilding with self.build array 0 length minus 1. For query, we test ranges like 0 to 2 or 1 to 3. With array 1, 2, 3, 4, updating index 1 to 5 gives a new sum. Running queries shows updated ranges. Let's break down how each line updates and queries the tree. Imagining a live data stream. To wrap up this deep dive into segment trees, we've learned what a segment tree is, mastering its ability to handle range queries efficiently compared to arrays. We implemented a segment tree using an array, explaining every line of build, query, and update, and tested it with practical sums. We applied it to a running sum tracker, seeing how it adapts to changes step by step. Segment trees excel in competitive coding or real-time analytics, and Jupyter's testing helped us nail each part. This sets us up for even crazier structures. How pumped are you for what's next? Before we sign off, let's think ahead. What if we added lazy propagation for range updates, or used it for minimum range queries? Picture a game tracking player scores. Segment trees could optimize it. We'll dive into these in future episodes, but for now, practice. Try a larger array or different queries. Jupyter's your playground, so experiment away. That's it for Part 10, Code Pilots. You've mastered segment trees with line-by-line insights. From theory to coding and beyond. Like this video, smash that subscribe button, and drop a comment with your ideas or next topic wishes. The journey's getting wilder. Next time, we'll tackle more data structures. So stay tuned, keep coding, and catch you later.